Hi everyone, welcome to your lesson on layers of the atmosphere and winds. So this first portion about layers in the atmosphere is review from stuff you've learned in middle school, and we're going to go a little bit deeper with both layers of the atmosphere as well as winds. And so part of it will be review, and then part of it will be new material added on to what you already know. I'm going to start with a review just to kind of refresh your minds about the different layers of the atmosphere. So the atmosphere is divided vertically up and down into 4 layers based on temperature. The layer, I'm going to start as if we are standing on Earth and move up away from where we're standing. So the layer where we're standing is the troposphere, and that's the layer where weather occurs and is closest to the Earth's surface. The stratosphere is the layer above that, and that's where the ozone layer is located. And in the stratosphere, temperature gradually increases because the ozone absorbs the ultraviolet rays from the sun. And because the ozone absorbs the UV rays, that's what makes the temperature increase. The next layer above the stratosphere is the mesosphere. And in the mesosphere, temperature decreases as you go up with altitude. So the higher you get, the colder it gets. And the reason that the temperature decreases in the mesosphere is because there's not ozone to hold that heat in. In the thermosphere, which is the layer above that, getting farther away from Earth's surface, is the temperatures in the thermosphere, in the outermost layer, increase again because now we have a ton of oxygen and nitrogen absorbing solar radiation. So that's heat from the sun. So that's making it heat up once again. Okay, so here's a diagram of everything I just talked about. So we're at Earth's surface and we are going in the troposphere. We are at about 10 kilometers and we are going from about 70 degrees, and as you go up in the troposphere, it gets colder. So if you look at the picture of, or the little diagram at the bottom of Mount Everest, it has snow on the top. So in the troposphere, the same thing happens as in the mesosphere. When you go up in altitude, it gets colder. So the higher up on a mountain you hike, the colder it gets. In the stratosphere, however, you see the red line shifting towards the other direction, towards the right. And because of that layer that you have, that orange layer, that's the ozone, that traps heat. So because the ozone traps heat, you've got temperature increasing. You also, if you skip the mesosphere and go up to the thermosphere, you have temperature increasing again, and that's because the air molecules in the thermosphere absorb the sun's solar radiation, which makes the temperature increase. Here's another diagram just showing you a different kind of visual to help you understand it better. The troposphere is the layer that is surrounding Earth. That's where all the weather across the globe happens in the troposphere. The ozone layer is only located in the stratosphere. Then you have the mesosphere and you have the thermosphere. Again, UV protection by the ozone layer. So the ozone layer lets UVA rays through, but UVA rays, it traps a lot of the UVB rays. The UVB are the bad UV rays that are most harmful to life. And so part of the job of the ozone layer is to trap those rays. Good ozone is concentrated in the stratosphere, and bad ozone is found in the troposphere and leads to a number of problems. So I know we've talked about this saying before, but it's good up high, bad nearby. So when ozone is in the stratosphere, which is higher than the troposphere, it's good. And when ozone is in the troposphere, which is where we are, where weather occurs, it's bad. And the reason for that is because it can cause a number of breathing problems, asthma, all sorts of different health problems from ozone being located too close to the surface of the Earth. When it's up high, it actually has a purpose, and that is to trap the bad UV rays. Okay, so shifting gears just a little bit from layers of the atmosphere, we are going into wind. And wind is the result of horizontal differences in air pressure. So left and right, differences between different pressures going on left and right. And air flows from areas of higher pressure to areas of lower pressure. So the ultimate energy source for wind comes from solar radiation, that's from the sun, from unequal heating of the Earth's surface. Unequal heat distribution across the Earth generates different pressure differences. And when you have different pressure differences, again, the wind will go from high pressure areas to low pressure areas. And that's because there's different levels of solar radiation across the surface of the Earth. The Coriolis effect, which we've already talked about, only influences the direction of the wind, but not actually the speed of the wind. So if you're in the northern hemisphere, it's going to cause it to shift to the right, and if you're in the southern hemisphere, it's going to cause it to shift to left. But the Coriolis effect does not affect the speed, it just affects the direction. So here's another visual for you showing you that north of the equator, which is the northern hemisphere, it's veering off to the right. And south of the equator, which is the southern hemisphere, it's veering to the left. That's if you were standing at the equator and looking at it. So there's two kinds of winds. There's local and global winds. Local winds are influenced by the topography of the land. So flat areas versus hilly areas are going to have different types of wind. And global winds are large currents of wind that, just like ocean currents, transfer heat from the poles and from the equator. So the heat coming from the poles is going to be colder compared to the air coming from the equator. So air from the poles brings colder, winds from the poles brings colder air towards the equator, and wind from the equator brings hotter air towards the poles, which sort of equally distributes the air across Earth. And we'll get to the pattern in just a second, but just like ocean currents, there's a specific pattern that winds take across Earth that's based on where they're coming from and what kind of temperature they're bringing. So if it's from the equator, it's hotter and it's less dense, and if it's from the poles, it's colder and it's more dense. The jet streams are fast-moving rivers of air that flow at really high altitudes. And so, just like ocean currents, this is basically an ocean current, but way up high in the air, and it's air and not water. Where you have centers of very low pressure, those are called cyclones, and centers of very high pressure are called anticyclones. And if you look at the left-hand side, it's a cyclone. That's a low pressure area. And if you look at the arrows, they're all moving in a counterclockwise direction. So they're moving counter to the left, like backwards around the clock. And if you look at the right-hand side, that's an anticyclone. That's a high pressure area. And all the arrows are moving to the right. So they're moving in a clockwise direction. So in the northern hemisphere, you have anticyclones, and in the southern hemisphere, you have the cyclones, according to the Coriolis. All right, so the types of global winds. There's trade winds, westerlies, and polar easterlies are the three that we're going to focus on. The trade winds are two belts of winds that blow from the east to the west, and the westerlies are the belts of wind that blow from the west. So all winds are named from the direction that they come from. So westerlies come from the west. Polar easterlies are winds that blow from the polar high toward the subpolar low, from the east direction to the west. And in the United States, all weather travels from the west to the east. So if you look at this diagram, you see, let's focus just north of the equator in the northern hemisphere. You see the trade winds blowing from the east to the west. You see the westerlies, which are the purple arrows, blowing from the west to the east. And you see that's where the United States is. And that's why weather in the United States travels from the west to the east, is because we're affected by the westerly winds. The polar easterlies, which are the yellow arrows up at the top, those come from the north, from the pole, and they blow from the east towards the west direction. And then it's opposite in the southern hemisphere. So same color arrows, same types of winds, just opposite directions. All right, so the last part of this lesson is on weather stations and the different types of symbols that are used to determine different factors of weather. So we've got temperature, cloud cover, dew point, pressure, wind speed. Wind speed's measured in knots, and 1 knot of wind is equal to about 1.15 miles per hour. So this is a full completed weather station, and you've got I'm going to start in the middle and work my way out. You've got the sky cover designated by a circle in the center, and depending on how shaded it is, will tell you how much cloud cover there is. So this doesn't have any shading, which means that it's a clear day. There's no clouds. The wind is designated by the line up to the left with the other 2 lines coming off. I'll go into that in just a second. Those are called barbs, and those tell you how fast the wind is blowing. The temperature is always off to the top left. The sea level pressure is always off to the top right. Air pressure is just directly over to the right. Weather is to the left, like is there any kind of precipitation, and then the dew point is the bottom left. So the center of the symbol again represents the cloud cover. That symbol that we just looked at had no shading, which meant it was not cloudy. If it's completely colored in, it means that there is total cloud cover. And the lines coming off the cloud cover determine the wind speed and the direction of the wind. So those lines again are called barbs, and they point in the direction that the wind is coming from, not the direction that the wind is blowing towards. That's something to really keep straight in your mind, because it seems like it would point to where the wind is blowing to, but it's not. It's pointing to where the wind is blowing from, which in the United States is the weather, again, always moves from west to east. And so when you are dealing with any kind of weather station in the United States that is telling you which way weather's going, it's always going to be west to east.